Clearly false. So this question is asking us to prove or disprove the statement, any endpoints on the plane are collinear. Well, the statement is clearly false. It's pretty easy to think of a counterexample. In fact, any set of n random points you think of, chances are they aren't collinear, so it's really easy to disprove. So instead, let's look at an example of a bad proof that tries to prove that it's true and pinpoint exactly where this bad proof goes wrong. So this bad proof is going to be a proof by induction on n the number of points. And hopefully from concepts or a previous class, you remember the basic steps of induction are your base cases, your induction hypothesis, and your induction step. So our base cases here are going to be when n equals 1 and n equals 2. And these are both actually pretty trivial, because when n equals 1, you can just pick pretty much any line, and of course it's going to be collinear with itself. And when n equals 2, well, 2 points are needed to define a line. So once you set down 2 points, you can just draw the line that goes through them, and they are collinear. So with those base cases out of the way, let's get started on the induction hypothesis. Since our last base case was n equals 2, this induction hypothesis is going to consider k greater than 2 to be some arbitrary natural number. And for our induction hypothesis, we're going to assume that any set of k minus 1 points on the plane are collinear. So this is the assumption that we're going to use in our induction hypothesis, so that our goal is to show, we want to show that any set of k points on the plane are collinear. So since this is what we want to show in our induction step, we're going to consider an arbitrary set of k points on the plane. And in order to make this clear, we can visualize a random set of k points. Also, to make it clear, we can give an ordering to these points. Visually, I'm going to say the ordering is going to be ordered by its position on the y-axis. So the first point is going to be this point up here, and the last point is down here, and ties would be broken arbitrarily under this ordering. So citing our induction hypothesis, we know that the first k minus 1 points must be on a line. So the first k minus 1 points are these points right here. Already we can see that this proof is kind of fishy because we have a counterexample and the first k minus 1 points aren't on a line. But for the sake of trying to figure out how this proof works, let's say we could totally cite the induction hypothesis fine, and these k minus 1 points are in fact on a line and they are collinear. Using the same exact logic, the last k minus 1 points are also on a line. So the last k minus 1 are these points, and they have to be on a line. And since the intersection of these two sets, the first set and the last set, is collinear, it must be the case that the union is collinear, so all k points are on a line. Of course, this proof is definitely wrong and breaks somewhere, so here's a good time to pause and try and figure out on your own where exactly it breaks. Okay, so hopefully you have some of your own ideas, so let's jump right in. A good starting point might be to take a closer look at that super sketchy step where we kind of just used the magic of slide animation to force the k minus 1 points to be in a line. So if we take a look at what those points looked like originally, we can see that the first and last k minus 1 points were definitely not in a line. So you might think that the reason this proof goes wrong is just that our IH is impossible to cite, because the first k minus 1 points might not be on a line. This is a pretty good guess, but it doesn't get down to the core of where this proof goes wrong. After all, when we consider when k equals 3 points, we actually can cite the IH just fine. When k equals 3, the first k minus 1 points, or the first 2 points, are of course guaranteed to be collinear, and similarly the last k minus 1, or the last 2 points, are guaranteed to be collinear. But despite being able to cite the IH, the total 3 points are not collinear. So where it actually breaks apart is the claim hidden in this line, so all k must be on a line. This sentence is implicitly trying to cite the property that when you have two sets of points, and the intersection of those two sets is collinear, then the union of the two sets is also collinear. And this property is actually totally legit, but it only works when the intersection has at least 2 points. And in this case, the intersection only has 1 point. So how can we guarantee that there were at least 2 points in this intersection? Well, in order to have that, you would need to have k greater than 3. But in order to have that, you would need the base case of n equals 3. And of course, we can't have a base case of n equals 3 because, well, it doesn't work out. So what's the takeaway in all this? After analyzing this whole proof and figuring out that it's wrong, You might think like, hey, it was really easy to disprove it, so why did we go through all that effort of recognizing where this proof is bad and where it went wrong? Well, there are a few reasons of doing this, a few takeaways we can get. The first is learning how to diagnose faulty proofs. Trust me, you will write a faulty proof at least once in your 251 lifetime, and you will be a lot happier if you diagnose the error before we do. Another takeaway is to be specific and clearly cite properties you use. So in this bad proof, they wrote the line, "So all k-points must be on a line," and they kind of hid the fact that they were citing that intersection union property. By clearly citing what properties you use, it makes it very clear when you're using them correctly. Along the same vein, it can help you make sure that you're satisfying the preconditions of the properties you're citing. If you write them down, you're more likely to notice whether or not you've satisfied those preconditions. Another takeaway is that induction proofs usually break early, so trying out a couple of examples past your base cases is a really good sanity check. And lastly, a common error in a lot of proofs is accidentally trying to take an element from a potentially empty set. How this came about in our proof was the intersection. What you were kind of doing is saying take 1 point from the intersection, then take another point from the intersection, and those define a line. Of course, if your intersection only contains 1 point, when you try to take another point from the intersection, you're picking from an empty set. So picking from an empty set is a pretty common error. Overall, we hope you get a lot better throughout your 251 career on these lessons, and best of luck.